All right, so let's start with XOR, which is here. We did modular arithmetic last time, the first modular arithmetic, and now we ought to do XOR. If you don't know your XOR, it's good to learn. So if you have a bit, then you can use XOR to combine two bits together. And this would be the plain text bit, and this would be the key bit usually. And so the rule is if the two bits are both 0, the answer is 0. If they're both 1, the answer is 0. If the two bits are different, the answer is 1. That's why they call it exclusive OR. It is this one or that one, but not both. By the way, when I first heard about this, I wondered why everybody used XOR. They don't use AND or OR, and there is a good reason. Let me make a little chart here on this page. If you make, let's talk about AND. All right, so AND would be 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. You know, 0 is false and 1 is true, traditionally, also in Python. So this is a true and a false. That's still false. Only 1 and 1 is 1. That's AND. And OR, by the same token, let's just copy and paste this, OR, combining two things where either one of them can be 1. 0 and 0 is 0, but all the other cases are 1. And these both are useless for cryptography because if you feed in data that is half zeros and half ones, and you pass it through this transformation, it turns into 3/4 0 and 1/4 ones. And that means information is destroyed. You cannot reverse the process. And the same thing is true here. The reason why the thing that became really all-important XOR is because XOR does not destroy information. If you feed in data that is half zeros and half ones, after encrypting it with XORs, it's still half zeros and half ones, because this one is 0. That means it is a reversible transformation and you can use it for encryption. These others are irreversible transformations. For example, if it turned everything to 0, that would clearly be irreversible. And even turning more than half of it to 0 is enough to mean there's no way back. You have mixed together some of these and there's no way to figure out which ones should be ones. So that's why this became the standard. And if you understand this at the bit level, then all you have to understand is binary to get the rest of it. So that's what one book does. In mathematics, they tend to use this symbol. In Python, you use the caret, shift 6, to do an XOR. So one bit is here. You can do 0 or 0, 0 or 1, 1 or 0, and 1 or 1. All right, so one way to look at it is the two have to be different, and that emphasizes the linguistic statement XOR. Another way to interpret this, which is probably more useful in most cases, is to think of it this way. Here's the plain text, here's the key. And the rule is, if the key is 0, leave it unchanged. If the key is 1, you flip the bit. Therefore, if you think about it that way, it's easy. What you've done is you've flipped half the bits in the data, which conceals it. And the point is, one thing that is now obvious, if you look at it that way, is if you repeat the process with the same key, you'll get back to where you started. So the encryption routine for XOR, if you repeat it again, it will decrypt. You don't need to write two separate functions. It's exactly the same process. It reverses itself. So that's a thing to know. So you can do 2 bits at a time. You just do the bits one by one. So 0, 0, and 0, 1. The 2 zeros make a 0. The 0 and 1 make a 1. So you never do, there's nothing complicated. You do the bits one at a time. Multiple bits just means you have multiple XORs. So you can do that in Python. You can do 0B for binary data, 0, 0, and 1, 0, and that turns into 2. Now, I'd expressed it in base 10. If I wanted it to be in binary, I'd put a bin in front of it, and then I'd get 0, 0, and 1, 0, and I get the binary version of it, 1, 0, because the first bit here is 0, and the first bit here is 1. Those are different, so I get a 1. The second bit is 0. The second bit is 0. Those are the same, so I get a 0. So that's what happens here. If I take 1, 1, XOR 1, 0, the first bit is 1 in both cases, so that becomes a 0. And the second bit is different, so I get a 1. And it drops the leading 0, and it prints it out here. So you can do 4 bits, same thing. You just do the bits one by one. XORing anything with all zeros will not change it, so you're going to get the 1000. Here, the first 2 are 1, and they combine with 0, so the 1s stay. The last one is 0, and there's a 1 there, so you get a 1, so you end up here. Here you have all 1s, and all 1s except the last bit. So the first 3 bits are all going to change to 0, because you have 2 1s, and the last one's going to be a 1. And here's another one. This is 5 XOR 10, if you go to base 10, and you can see the first and third bit are 0, and here they're 1. And the second and fourth bit are 1, and here they're 0, so you get 15. All the bits change to 1. So that's why it's a useful encryption routine. By itself, XOR is not very secure, because if you do single byte XOR with a single byte key, there's only 256 possible keys, but it is a part of very secure ciphers like AES, really strong ones. So you can do, and of course you can do this in Python if you like. You can also do it in base 10 in Python, but then it's harder to understand. Doing it in base 2, it's easier to understand how it works. All right. So let's try a few of these. Let me check for comments in the Twitch. There are none. Okay.
So
yeah.
So in order to do that, so in order to decrypt it, you need the key in the first place.
Yes, you need to figure out the key. Now, there are a lot of tricks to find the key. The simplest one is just try every possible key. If it's only a 1 byte key, there aren't too many. But if the key is many bytes, it could be hard. Another thing that's useful is if you have a large amount of encrypted data of computer files, a lot of computer files contain a lot of bytes that are 0. And if you XOR 0 with the key, you get the key. So if you just take the most common byte, that's probably the key. If you encrypted ordinary common computer files like Word documents and images.
So let's say we use these single keys. I'm just trying to figure out how it would work taking a piece of actual binary. When like you said, the binary for 15, if you have a key to convert it, will you use that key for every instance of 15?
Well, the way you usually do it, here, let me just write it up. We've got plenty of time here. Let me go to my Opera. Let's make one. A good idea. Let's have Colab. All right. So I have to sign in because Google likes to waste my time. All right. So let's make one. All right. So let's have plain text equals something. All right. Then we're going to have a key, which is going to be just anything like 15. And then we're going to do for a character. This will pull the characters out one by one. Now I'm going to have the number for C equals ord of C. And right now I'm just going to print COC and just see how it's looking. This should resolve the plain text into numbers. So let's just see how that looks. And this, like I say, is always the process. Write just a few lines and test it. Then a few more lines and test it. Then it's a lot easier to find your errors. So here I did something wrong. For C in plain text. Yeah, you're right. I'm missing the N. All right, good. Okay, so here's the letters and here's the numbers that match them. They're in base 10. So these are the ASCII numbers that match those. So now that I've turned these letters into numbers, and the key is already a number, now I'm going to say ciphertext byte. Yeah, so get rid of that O there. There's the ciphertext byte is not letting me do it. There we go. Is going to be OC XOR the key. And then now I'm going to make ciphertext. In fact, I'm just going to have bytes for that because it's going to be an unprintable thing. And I'll just print that out, ciphertext byte. So I'm going to put it here, and then I'm going to move that line down. So I print it after I do it. And there. And get rid of the extra space. Okay, that should do it. So here's the plain text, turned into numbers. Here's the encrypted stuff. The encrypted version of it is like that. And so these numbers are showing it, and it might be clearer if you print them all in binary. If I do bin of this and bin of this, then it should be easier to see what happened here. There. Let's see how that looks. Okay, here's the original plain text, and here's the ciphertext. And remember, the key was 15. So what I did was I flipped the last 4 bits of every byte. So the first 4 bits stay unchanged. The last 4, invert them all. So 0110 turns into 1001, 1111 turns into 0000, and so on. So that moves. One thing about that is these characters are probably still printable because I've only moved them by a maximum of 15. from a printable character in the ASCII space, so I might be able to actually print the answer. Let's try that. Let's try printing character sub OC. I think it's OC, let's see. Oh no, ciphertext byte, okay. That would be the printable character in another column, and we'll see if it's printable. And it is mostly. So it's what I have to do, make this smaller. Oh, it's printing things twice for some reason. I think some of them are turning unprintable, but I see I apostrophe or backtick Z. You know, it's turning into, most of them are turning into printable characters. That's what the ciphertext will look like. And if you wanted to get back from that to the plain text, you just do it again. You take print character sub of ciphertext byte. Whoa, there we are. Ciphertext byte to the key. There, that should give me a column that will be the original text coming back at the end by just doing the same XOR again. Now, I followed up somehow. Oh, not character ciphertext byte, just ciphertext byte alone. That's already a number. Like I say, I spend most of my life in Python moving data from one data type to another because of errors like this. All right. And there you go. So F, somehow it's not.
It should be at the very end.
Well, it should be at the very end, but somehow it isn't. So I'm going to put some labels in this. Decrypted. And then hopefully I can find it. It's wrapping around funny or something like that. There, here's the decrypted. Whoa. So that's disturbing. Ciphertext byte to the key. Oh, I need to print character of this. This is a number. I need to turn it back into a character. There.
Okay.
That ought to, wait, that's already down there. That's what I did up. Ah, okay. What's going on here? I got an extra print appeared out of nowhere. Maybe the AI filled it in or something stupid like that. This is where it should go. All right, that might work. There we go. And now you see the plain text appearing here, FOUR. So it scrambles into this binary thing, and somehow the junk is printing down there, which I don't quite understand.
That's the initial. If you scroll up,
What is this?
Scroll up, and you'll see that the.
Oh, it didn't. No, they. Oh, yeah, I have two print statements. I didn't mean to have two print statements. Okay, let's get rid of one of these.
The C, OC cipher byte. The C.
Yes, C, bin of OC. Here's the binary. Right. Okay.
Cipher byte 73 in the top line.
Right. So it's only printing the binary there. That's good. All right. This will be more clear. There we are. So on the left, you see the plain text. Here's the encrypted stuff, and there's the plain text created again by XORing it twice. So I hope that makes it more concrete. That's the idea. And you could crack this without knowing the key by just making a loop to try all possible keys and print out the answers until you see what you can read. And that's why.
Isn't it technically possible that two different keys can change a encrypted thing into two separate messages?
Can change it? Yes. Now that's a real important question you ask, and this is why the one-time pad is secure. This is something with all modern encryption schemes. If you try every possible key, like AES, RSA, all the famous encryption schemes, they have this property. If you have the wrong key, you get unreadable garbage, random numbers essentially. And therefore, all you have to do is try every key until you find something you can read, and now you win. But if you use the one-time pad, where you use a different key for every byte, and it's no pattern, and you try to break that by brute force, the one-time pad, using all possible keys, you will generate all possible plaintext. All the readable plaintext with that number of letters will appear, and you have no idea which one is the message. That's one of the reasons why the one-time pad is essentially perfectly secure. If you can't steal the pad, you're hosed. There is no pattern to analyze. There's nothing you can do. But this thing, you keep using the same key over and over and over, then there is a limited space and you can try it all. All right, that's good. Let me check for comments in the Twitch, and there are none. All right, so let's try a few of these XORs, see how you do at it. Here's the part where you have to get 5 or 10 of them in a row to get a flag. All right, so what's 13 XOR 2? Might be a little hard to do in your head. Okay, I think I got it. It took me a while. Okay. Any of you folks got it? Well, let's work on this one together. All right, so what is 13 in binary?
It's 1101.
It is.
So it's
Oh, no, wait, that's right. This is 4, 8, 4, that's 12, 13, right. Okay, what's 2?
It should technically just be, oh, that's not a, wait, is that a 2? Because 1.
That's 13. No, this is 13. 8 plus 4 is 12, and 1 more is 13. So what's 2?
Shouldn't it go to 0010, which would be a 2, but it's not.
That's right. 0, 0, 1, 0 is 2. So when you XOR those together, what do you get?
Oh, okay.
That's how it works. So what do you get when you XOR?
You get a 0000.
No, you don't. If the 2 bytes are different, the answer is 1. That's exclusive
Oh,
OR.
okay, I got it back.
So this is 1, yep. What you've got,
So it's 15.
yeah, what you're doing is X and, but this is XOR. If the bytes are different, the answer is 1. So you get 15. So I was getting it wrong in my head, by the way. So the right answer to this one is 15. All right, how about 8 XOR 14? Let's work on it over here. So what's 8?
8 is just the, it's 0100.
Any comments?
That feels about right.
What's that?
That feels about right.
Yeah.
I don't think it is. What is, this is the 1s, right?
Oh,
That's the 2s, this is the 4s.
0101.
No, 0101 is not 8 either. Because, there's a simple answer, this is an odd number and that's an even number. And the even numbers stay even in base 2. No, this is the number 1s, right? This is the number 2s, this is the number 4s, and that's the number of 8s.
Oh, so it's 1000.
That's right. So their 8 is 1000.
I always get it confused because I'm used to it being, I always had it memorized as imagine to the power of 2. So the first digit is going to be 2. And so then I have everything shifted over in my head by 1.
Yep, well, it takes practice. How about 14? What's 14?
1110. Because
That's it, because
13, so
it's 1 less than 15, right. So now if you XOR them, what do you get?
0110.
And what's that?
6.
Right, that is 6. So 6 is the answer. That's how you do it, 6. All right, how about 8 XOR 1? Might be able to do this in your head.
111 or 1001.
And what,
which is,
that's that in base 10.
that'd be 9.
That's right, because this has 1 bit on the left of the nibble, this has 1 bit on the right of the nibble, so you get both of those turned to 1. And I'm going to write it down here to make it clear to anybody that hasn't got it. The 8 we've already done, and the 1 is, so the answer is 1001, and that's 9. All right, let's do one more, 8 XOR 6.
So 8 is already done. 6 is just the 2 middle ones.
Yep, so that's,
0110.
Yep.
So that becomes 1110.
it does, doesn't it? And so what's that?
Which is 14.
That's right. You got it. That's 14. All right, that's what I wanted to show you. So you should practice with your XOR until you understand how it works. It's good for you. And all,
I'm good at logic things like that.
yeah, and all math is like this. That's why math should be fun. It should not be frustrating. All math is,
Math is the one subject I excel at, and it's the only reason why I'm good at coding for the most part.
well, that's good. They're very closely connected. But a lot of people in America are afraid of math because they get taught it in an abusive way. But the fact is, it's just as easy as games you play with cards and dice. You just flip little things around in a pattern and figure out how they work. All right, so I'm going to stop this recording.